Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 6.1.3, which is Connecting Special Right Triangles to Trigonometry. Before we dive into the lesson, I do want to take a second and review our special right triangles. We've covered two of them in the previous lesson. The first off was the 45, 45, 90 right triangle. So I'm going to write that down here, the 45, 45, 90 right triangle. Sometimes people call this the isosceles right triangle. And so the way the side ratio breakdown worked for this one was that because the triangle was isosceles, the two sides ended up being the exact same length. So they were both x and x. And we found through pattern recognition that this side ended up becoming the square root of 2 times the side of each of the legs. And so that ended up being the pattern that we established for the 45, 45, 90. The 30, 60, 90 was a little more complicated, but not terribly, to where you probably wanted to establish that the opposing angle was what it was supposed to be. So in this one where the 60-degree angle is on the base, we put the 30-degree angle on the upper angle here. So contrastly, I'll go and put the 60 on the upper angle. And what we realized through the proof was that opposite the 30-degree angle was the shortest side. We always called that side just x. It was just some value, right? Opposite the shortest side would be, opposite the shortest angle would be the shortest side. The medium angle was the 60-degree angle. Across from the medium angle was the short side times the square root of 3. So, of course, when you multiply something by rad 3 is about 1.7, so you're making it just slightly larger. And then the hypotenuse, which is opposite the 90, was always going to be double whatever that short side was. And so that's one version of this diagram of the 30, 60, 90 right triangle, where the 60-degree angle is on the ground. But when the 30-degree angle is on the ground, again, opposite the 30 will be the shortest side. We call that x. Opposite the 60 is going to be the x rad 3. And then opposite the hypotenuse is going to be 2x. So how do these patterns register, and how do they correspond to their trigonometric counterparts? When we think about trigonometry, we think about the Pythagorean theorem, we think about sine, cosine, and tangent. Now, to establish the special right triangles, we did use a lot of Pythagorean theorem, but how does that connect with sine, cosine, and tangent? Well, that is going to be manifested in these problems down here on 6-25. It says, copy the triangles at the right onto your paper and label the missing side lengths and angle measures. And then we'll use the diagrams to show what each of the values are. So let's go. So opposite the 30 on this 30, 60, 90 right triangle here, which is A, B, and C, opposite the 30 is going to be 1, which means opposite the hypotenuse is going to be double of that 1. So I'm going to call that 2. And then opposite the 60-degree angle here is going to be the medium side angle, medium side is going to be 1 times rad 3 or just rad 3. Looking at this 45, 45, 90 right here, this guy's got to be 45. He has no other option. Of course, DE is going to be 1, and EF is going to be 1 times the square root of 2 or just rad 2. So now that we've got both of these special right triangles filled out, let's go and see if we can't figure out what some of these values are going to be. And so from here, what I'm going to do is I'm going to go and just figure them out. So sine of 30, well, that references me to the ABC triangle. So sine of 30 is going to be opposite of hypotenuse. So from this angle's perspective, 1 over 2, looks good to me, 1 over 2. Sine of 60 is going to be, again, referencing this ABC triangle here. Opposite the 60 is going to be rad 3, hypotenuse is going to be 2. So this is going to be rad 3 over 2. I think I'm going to write it like this from now on, that way I have more space. Sine of 45, that's going to be looking like my EDF triangle here, which is going to be, looks like opposite of hypotenuse, so 1 over rad 2. 1 over rad 2. I'm going to talk about that in just a second. I'm not going to leave the answer like that, but there's going to be another 1 over rad 2 at some point, and we'll go there when we need to. Cosine of 30. So back to the ABC triangle here. Cosine of 30 looks like adjacent over hypotenuse is going to be rad 3 over 2, so equals rad 3 over 2. And feel free to pause and try and get these answers before I do, and then we'll go from there. But if you feel like staying with me, then we'll head over to cosine of 60, which is going to be right here. So again, 1/2 based on adjacent over hypotenuse. Cosine of 45. Notice how it doesn't matter which 45 I use, right? Either way I cut it, if I go from the top 45, I'm going to go adjacent over hypotenuse, or I'll go adjacent over hypotenuse from the angle E. Either way you slice it, I'm going to get 1 over rad 2. Again, I'm going to talk about 1 over rad 2 in just a second. Tangent of 30. Tangent of 30 is going to be, looks like opposite over adjacent, so 1 over rad 3. I'm running out of space there, I apologize. 1 over rad 3 right there. Tangent of 60 is going to be opposite over adjacent, so rad 3 over 1. And then tangent of 45 is going to be opposite over adjacent here, which is 1 over 1. But we knew that from a couple lessons ago. Okay, so let's talk about this for just a second here. I want to bring up one idea for you guys here, and it has to do with those 1 over rad 2s and the 1 over rad 3. This notion is called rationalizing the denominator. Now, it's kind of I consider it more of a courtesy than it is a rule, and so at this point, one of the things that, one of the customs that you want to get used to in mathematics is the notion of irrational pieces being in the denominator. And as a custom for simplification, we tend to not do it, at least not at this level. There will be times in later math classes where leaving a radical on bottom is perfectly fine. In fact, I consider it a very good idea in those upper math classes, but we're not there yet right now, and we do want to learn how to rationalize the denominator, because it is a very valuable mathematical idea that helps make things easier later on down. So when it comes to rationalizing the denominator, the notion of this maneuver here is getting rid of any irrational expression in the denominator. And how do we do that? Well, from here, we're going to look at 1 over rad 2 for a second here. So if I say sine of 45 equals 1 over rad 2, if I look at the notion of 1 over rad 2, if I want to get rid of the denominator, of the radical in the denominator rather, I'm going to go ahead and multiply the bottom by rad 2. And the reason why I'm doing that is because rad 2 times rad 2 is rad 4, and rad 4 is just 2. So notice by doing that, I've gotten rid of the radical on bottom, so my denominator is now rationalized, right? Problem is I can't just multiply the bottom by rad 2, because if I do that, then I'm changing the value of the number. So what I do is I multiply the top by a rad 2 also, because rad 2 divided by rad 2 is 1. And if I multiply something by 1, I am not changing the notion, the nature of that number. So 1 over rad 2 can be expressed as rad 2 over 2 when we rationalize denominators. So I'll go and do that for sine 45 and cos 45. Looking at tangent of 30, again, so tangent of 30 is 1 over rad 3. Well, if I look at 1 over rad 3, again, I'll just rationalize the denominator here. I'm going to go and multiply the top and bottom by the square root of 3. Because again, the square root of 3 over square root of 3 reduces to 1. And again, multiplying by 1 is not changing anything. So I'm going to go ahead and do that. So I got rad 3 over 3, which means that's what this guy is. And I'm actually officially out of space up there. So I'm going to go ahead and pull him aside this way. And that's rad 3 over 3. I will expect you all to rationalize denominators from now on, now that we've gone over it. But that's the technique right there. we will see that happen more often as we advance forward. Give me a second, I'll be right back with the next set of problems here. All right, in 6-26 here, we're going to examine this diagram at the right here, which is the right triangle with dimensions x laterally, y vertically, and 1 hypotenusely. It says write an equation for sine theta and cosine theta. So I know that in A, if I do sine of theta, that's going to be the opposite of hypotenuse. So that's going to be y over 1, or just y. Cosine theta is going to be adjacent over hypotenuse. So that's going to be x over 1, or just x. And so here are my two equations for sine and cosine. Now, hopefully that should make a little bit of sense, where we have cosine being x and sine being y. Just because with the hypotenuse being 1, the x value would be almost the horizontal value on the x-axis if we were to look at this as the coordinate plane. The y would just be the y coordinate or the y axis. And so that's why sine is usually associated, actually not usually, most of the time, associated with the y value. Cosine is associated with the x value. You'll get more into that in your next math class. But now it says, using the results from part A and your knowledge of right triangles, what is the value of sine squared theta plus cosine squared, or sine squared plus cosine squared? So if I know sine squared plus cosine squared, well, I know that that's going to equal 1 squared. How do I know? Well, it's because sine of theta is y, so y squared, right? Plus, I know that cosine is x, so that's going to be x squared equals 1 squared. So it looks like y squared plus x squared equals 1, which means I'm pretty sure that sine squared plus cos squared equals 1 somehow. Now, it says, does the relationship appear to be true for all angles? Use your values from 6-25 to calculate the sums below, and then we're going to write down our findings. Okay, so let's see if we can't demystify this somehow at all. Sine of 30 squared plus cosine of 30 squared. Well, if you look back up at the table, I think you're going to find that sine of 30 is going to be 1/2, and that's squared, plus cosine of 30, if you remember back from the table, and again, I encourage you to pause and look at the table you have in your notes, that is rad 3/2 squared. Well, how do we solve this? 1/2 squared is 1/4 plus 3/4, which is 4/4, which is 1. Hey, sounds kind of familiar. We hypothesized that sine squared plus cosine squared equals 1. I believe the next one was 45. Yep, so sine squared 45, so sine of 45 squared. Now, I want to introduce you guys to a little bit of a new notation here. It's not uncommon that you might see cos squared of 45 here. This notation here means that you're going to take cos of 45 and then square him afterwards. These two mean the same thing. Sine of 45 all squared is the same thing as sine squared of 45. And so I just want to make sure that we are aware of different kinds of notation. That way we can be comfortable with both. Let's see. I believe they were both rad 2/2. And if I square them both, I'm going to get 2/4 plus 2/4, which is 4/4, which is still 1. Now, if you're wondering, wait a second, what if I use the unrationalized version of this, right? We just learned how to rationalize the denominator. Maybe it's a trick that I'm trying to show you just so I can force 1 into the issue. Let's see what happens. If I do the unrationalized versions, remember these guys, 1/rad 2? If I square them, I get 1/2 plus 1/2. I seem to get 1 either way. So, interesting kind of scenario here where it seems like, for now, at least with these special angles, if I square sine and I square cosine, as long as the angle is the same, I seem to get 1 every single time. Let's see if that holds true for all angles. I'm going to go to the next problem. Give me a second. I'll be right back. All right, so in 6-27, it says, testing examples as you did can give you a general idea if a statement is usually true, but in order for it to always be true, we have to have a general case. And so what this problem is asking us to do is it's asking us to use some generic angle called theta. And if we can prove this to be true for some generic angle called theta, and using symbology, then we can prove this to be true for any angle possible. So it says, first off, write an equation about the side lengths of triangle ABC at the right, which is this guy, and explain how you know it's true. Well, if I had to just use a trigonometric relationship with a right triangle using only the sides, the only thing that I could guess would be that a squared plus b squared is equal to c squared. That's the only thing that I know that I know is true, and that's because of our good old buddy Pythagoras. So this is the Pythagorean theorem. All right, so we know that to be true. Now it says, now you will prove that sine squared theta plus cosine squared theta equals 1. We have to write an equivalent expression for sine theta squared plus cosine theta squared. So what do we know? Well, I do know that sine of theta is equal to, looks like a over c, right? Again, opposite over hypotenuse. And I know that cosine theta is equal to b over c. How do I know that? It's because of adjacent over hypotenuse. Well, what I'm going to do is I'm going to actually square both sides. So if I square both sides, what I get is sine squared theta equals a squared over c squared. Right, because if I square a fraction, I'm going to square the tops and bottoms individually. So if I do that, so I'll do this here, same thing. So from here, cosine squared theta is equal to b squared over c squared. Now it says write an equivalent expression for sine squared theta plus cosine squared theta using ABC. So again, now that I have a squared relationship between sine and cosine with their respective sides, I'll go ahead and say sine squared theta plus cosine squared theta is equal to, now in this case, since they are equivalent statements to the a squared over c squared and b squared over c squared, I'm going to go and call them a squared over c squared plus b squared over c squared, right? Like this is linked to this guy, this is linked to this guy, right? So, one thing plus another thing is equal to their equivalent parts being added together. Hopefully that makes a certain degree of sense. And now it says rewrite your expression for part b without parentheses. And can you write as a single fraction? Okay, I don't know where the parentheses came in handy, but sure, we can do that. So from here, I can say sine squared theta plus cos squared theta equals, because they have the same denominator, I'm going to go ahead and combine the numerators together and create a single denominator. Now, as this problem starts to look worse, we have to start to look back at our original expression here. And it says, rewrite what is your expression equal to, justify your answer. Well, at this point, this hardly proves anything equaling 1. And remember, our objective was to show that sine squared theta plus cosine squared theta equaled 1, right? But how are these things the same? Well, remember, going back to the initial relationship in part A, they asked us to use a Pythagorean relationship, and we know that a squared plus b squared is in fact c squared. Well, do I see that relationship happening at all in part C? Well, I should, right? Because this a squared plus b squared is right here, right? And based on the relationship we established in part A, I know that I can replace this thing that I just highlighted in blue with a head-on c squared. Now, that c squared that's on bottom doesn't go anywhere. And c squared divided by c squared, or anything divided by itself, is 1. And that the whole time was still equal to sine squared theta plus cosine squared theta. So what we have proven right here, this is what is known as the first Pythagorean identity right here. Let's go and write this down here. Pythagorean identity. And it will be the first of many Pythagorean identities that you guys will use when you get into integrated 3 and you get into really interesting aspects of trigonometry, and I'm really excited to see what happens when you guys encounter that. But for now, that is the lesson into how right triangle trigonometry is associated with those special right triangles. Hope you enjoyed this. Hope it was helpful. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.